Hello everybody, I am Fadil. I'm working under additive manufacturing field for the lattice structure designing and optimization. So here I would like to present a new finite element tool that can help for the lattice structure analyzing and designing. First of all, I would like to go overview for previous published work for the lattice structure engineer. So first work was for three types of the lattice structure. So first one was tetra configuration. So this one for unit cell tetra, and this one for the entire configuration, and this one for the printed one. So this one for tetrahedron and this for unit cell. If you see, they are very similar, but here we have horizontal struts, and this one for the entire lattice configuration, and this one is printed spacement. Here for pyramidal has square base, and this one for the printed one. So all these printed samples were tested under quasi-static axial compression test, and we capture the following figures. First one for the tetra configuration. So we have progressive damage is clear, can be seen here, and this pictures for the progressive damage. So this at first peak, when first failure happen here for some layers, and this drop down and can see the progressive damage. Second one for tetrahedron configuration, you can see different behavior for progressive damage, and this one for the pyramidal. We have another study here for BCC configuration. As you see, this one for unit cell, and here the building the configurations. And to enhance these configurations, so we add some vertical struts here. This for BCC, and here we adding vertical strut at every node. Here to see, here we have vertical struts in layer by layer, and this one called BCCA, and here we have vertical struts distributed in gradient. So all these configurations were tested in compression and quasi-static axial compression. So we got this progressive damage, and this one reached about 500 Newton before failure, and build new configuration and failure, as you see here. All of them tested, and we capture all these plots for progressive damage. So we are interested to study and analyze all this configuration computationally by using finite element. So Abacus is most proper software, commercial finite element software for this reason, and efficient, especially for capturing the post-yield and progressive damage. However, to create these configurations in Abacus is tedious, costly in time and effort. So first you want to create these parts, and you want to do some partitioning that you can apply the hexahedron mesh and applying the boundary condition, and you need to select all of these faces to make like attraction or some stuff like that. So all this is challenging to be done in Abacus. For this reason, I create and develop a new Python code. This one can take all the parameters and do all these tasks. So probably in next video I will try to explain how this code working, but now in this video I will focus on how this code work in Abacus. So when you go to Abacus, here you have plugin. So I create icon under my name Fadil, this one was cited and similar to micromechanics plugin. But micromechanics is limited just for one and limited in conditions. So what Fadil doing? Let's hit Fadil. So we'll see this one interface. So I designed all this one and this one input the parameters. So here you can introduce the university, right side university, and mechanical and material engineer. I call this tool Lattice Structure Design or LSD, designed by Abdul Salam Fadil, and this is my email under supervision of Professor Hassan Mian and this email. So what LSD doing is designing and creating different types of lattice structure. First one, we have BCC, BCV, BCA. They are from same family, and we need to input all these dimensions for unit cell. Second one, we have tetra and tetrahedron, same family, and they are distributed radially. We will see that. And third family is unit cell for perimeter. So here I divide three groups of parameters. First one BCC, BCV, BCA, and this one tetrahedron or tetra. This one for perimeter. So here you can select the configuration type BCV, BCV, ABCA, or which configuration you are interested. For example, I will pick tetra. Here you can pick the materials. You can apply ABS, titanium, or any material you want, or any other material if you want to apply other materials not available here. So when you select tetra, you have to go to this group. So here you can input the number of radio level, because this one is distributed radially around circularly, and this one number of level at height. So this one number of cell in height in z direction, you can say by other way. This one the dimension for side length, and this one for dimension for height length. So now we will work in default state and hit OK. Just wait. So now see, it's very quick. We got all this configuration under the boundary condition. I will go to see how this part looks like. How this one for tetrahedron parts. So this one, the unit cell, as you see, distributed in one radio level. See, and this one partitioning, and you can see here the mesh. We could apply the hexahedral mesh, which is brick elements. This element is very efficient element for capturing the post yield and fracture criteria. Now I will try with different parameters. Now we apply with single radio level. I will try with 2 radio level. Let's go back to Fadil. I will select again tetra. I will change this number to be 2. I want to see what the difference between single and 2 radio level. Okay, and hit OK. This will take a little bit longer because more unit cell will be patterned. Okay, let's see now for assembly. See this one became bigger. Let's see the part, how part will be looks like, and see. So this one first radio level, second radio level, and this one has been partitioning and applying with all the boundary condition. I will try with different configuration. Let's try with BCC. I will make it little smaller. Okay, for the BCC, here the dimension, and here the number of cell at X direction, number of cell at Y, number of cell at X. This one to create the entire lattice, and this one the length of one unit cell. can change the strut radius if you want. You can change the material if you want. Okay, now let's see how this one will be look like. Let's see now. For the assembly, I created 2 by 2 by 2. I will go to part to see how this one look like. See, 2 by 2 by 2, and now we have the mesh, perfect mesh and converged mesh, very perfect and very efficient mesh. Other benefit from this software, if you go to attraction, here we apply the boundary condition to make this rigid to be stuck with the model. So if you do this one manually, you have to select all these faces. For example, this one for 1 unit cell, you have 8 faces. For entire lattice, you have 32 faces. So if you select this one manually, is very tedious and hard. So this one is created and applied by the code. Moreover, if we go to load to see boundary condition is applied, is assigned also. You can see the property, you can see the material. All the material is applied with all the fracture criteria are applied. So for step also is applied for entire thing and ready to be run. If you go to a job here, see it's ready, you just submit. So when you submit this job, this will take a while for running. After that, you will see the following result. I summarize result just for hexa for the tetrahedron. So here I have the tetrahedron at initial stage, and this one for XYZ plane, X and plane. This one for section to show the entire view. So when you apply the boundary condition, so we could capture the progressive damage at every stage. At this one first stage, at this point for Yale, and this one other stage, and the plateau stages. And here I can show, we can see the agreement in the fracture behavior at this stage between the experimental and finite element. See, it's very similar. So fracture happen in these sites. Oh, that's strat. You can't. All the stages capture, and this one, see, almost before the densification and the densification stage. So by this finite element tool, we became able to find for all these configurations with all the dimension, with any dimensions or parameters you want. So here I will hit cancel. I will open new file. I would like to do some interesting inputs. So if pick tetra and make this one smaller, I will keep this one, but I want to change the side length to make this side length smaller and make this height higher to shrink this configuration. Okay, shrink to this cell out. If I input 2 by 5, let's see how this one will look like. Okay. See? Okay. See, I could shrink the cell down and see the cell became, this one is 2 by 2 by 2, and this one is 5, and this one is meshable with hexahedral mesh. And so to conclude this video, so this tool is beneficial and useful for studying different type of lattice structure with different dimensions, with different angles of struts, for different materials. If you have a question, please leave comment, or you can send an email to me or to my advisor. I will try in next video, I will try to explain more how to use this tool.